Hello, welcome to the final lecture series in kinematics where we are going to look at special case studies of projectile, which is generally what happens when you throw an object at an angle. And you've been doing a lot of throwing in your life, whether you know or not. And by the way, speaking of throwing, there's a troll here. Okay, and this is actually a short clip from Lord of the Rings, and in it, I want you to observe all the projectiles that is happening.
Send these foul beasts into the abyss! Stay where you are.
While watching the video just now, you probably noticed all the projectiles flying around, right? There were so many slingshots shooting up, and finally the troll can calculate the exact time where the projectile is heading towards him and step aside. Well, this is what we're going to do today, or rather we're going to do it on paper lah. Whether you can do it while the boulder is coming at you is a totally different story. So far in our journey in kinematics, we have learned to use words or terms to describe motion. We have learned our Stuva equation, and we have learned how to do graphing. So we have already applied this in two different type of cases. One is the old vanilla type where there's no gravity. We just look at horizontal linear motion like the train questions. The second type will be vertical linear motion. So for example, you can either release a ball or you throw a ball up and it falls down, all kinds of free fall, all right? Or that bouncing one, okay? So today we're going to level up and combine both horizontal and vertical motion. Okay, so this is what we call two-dimensional motion. You got X, you got Y. So the X will be horizontal and the Y would be vertical. Okay, so just to remind you of the vectors that we have studied in the previous chapter, I'm going to sketch out the horizontal component of velocity, let's say Ux, and also vertical component of initial velocity, let's say Uy. So if you look at this one, you will notice that I can combine these two vectors, right? And then what we will get, as you can see, this is from chapter 1 when we studied vectors. When I combine both vectors, I will get a resultant vector that is at an angle. So it's a little bit like that slingshot when it's throwing the boulder. It will be thrown at an angle from the ground, okay? So you can see if I combine Ux and Uy, I'm just going to draw two different diagrams just so that you understand what is happening. So the resultant based on the first diagram, we can use the top to tail method or the vector triangle method, where the resultant, the green color resultant, let's say U, will be equal to Uy plus Ux. Okay? So it will be thrown up at the angle theta from a certain direction. And this one, if you don't want to draw a vector triangle, we would draw a parallelogram. And this is actually what we will draw along the trajectory of projectile motion. So projectile is when you throw an object at a certain angle from the horizontal and the object would travel across a range towards you. All right, Ux like this. Okay, so this is your Ux. And let's say now I throw a ball and release it at an angle U. So the angle theta is measured from the horizontal theta. Okay, and the next part that we're going to draw is to think about the trajectory and also a bunch of graph. So at this part, I'm going to show you a recording I did with Miss Ellie.
Previously, in kinematics, you have learned how to draw graphs like this. You have also learned how to calculate kinematics, what is projectile. So now it's time to level up. How do you draw more complicated graphs? So I have for you today's challenge scenario is me trying to throw a basketball. So I'm going to throw a basketball. I want you to observe the path very carefully. It will only happen once. So let's take a look. How does the path of a basketball look like? Some of you say, miss, I already know. I play basketball every day. Yeah. Take a look. Alright, so I'm going to throw, whoop, bam, and stop. Okay, so the challenge for this video is, how do you sketch the acceleration, velocity, and displacement graph for both components? What does both components mean? Oh, reminder, both components mean you have your x component, the horizontal component, and well, kind of like that. I can see lah. And the y component, also known as the vertical component. So if I trace out the path of the basketball just now, let me see if I can use a red color, brighter a bit. From my hand somewhere like that lah, and then pop. Not as nice curve. Well, you get the idea. So this is what we call a projectile. Okay, you know how to calculate stuff with this. You can use your Stuva kinematics equation. But how you draw the graph for this thing? First things first, you need to think of both components separately. X is X, Y is Y. Horizontal velocity, vertical velocity is vertical velocity. They don't affect each other. So if you have x v, I should say vx, then you have a vy. Remember this picture? Okay, you break at every point you can break the velocity down into its components. So how are you going to graph that? First things first, I'm going to give you a hint. We're going to look at one animation. Let me see if I have it with me. Yeah, I do. So this animation here I want you to look at the same thing that I did, but throw the basketball a curve like that. But pay close attention to what happens to the velocity vectors here. So here v is the main velocity of the ball, but it can be broken down into the horizontal and the vertical velocity. So let's also crank the speed down so you can stare carefully. First one, I want you to pay close attention to what happened to Vx. Okay, Vx is this one. So pay close attention to the length of it. Let's fire. Pooh! Is it changing length? Is it getting shorter? Is it getting longer? Oh, look! Vx is not changing at all. Write that down as a note for observation. We're trying to be scientists here. Next one, okay, so Vx, interesting, not changing. Why is that? Vy, pay attention to this one here. Okay, this is our projectile, and it's going up at some vertical velocity. Let's pay close attention to Vy. Let's fire. So you're going up. Oh, the arrow's getting shorter. And oh, now the arrow's pointing down. Wait a second. We have seen that pattern before in another animation somewhere. You remember it? Okay, so one last time. Now look at both together and see how they contribute to the V, the total velocity. Now this is going to go really slowly. So as you go up, okay, to summarize, Vx is not really changing, but Vy is getting smaller and smaller. Why is that? Think about it. Acceleration. So Vy is affected by gravity. Okay, the vertical gravity is trying to pull stuff down, but the horizontal is just going along, and this is assuming that there are no air resistance that we take into consideration. Okay, so yes, that is the simulation, how to think about vectors. Now from this diagram and this case study, we will need to draw graphs. So let's go. Okay, so yeah, this is our graph that we looked at. Now, how do you graph the x and y components? There's some space in your notes for you to draw graphs along with me. You can try guess what they look like, but we'll be drawing them together. Ta-da! So you have acceleration, velocity, and displacement of the vertical component. So first one, let's start with acceleration, shall we? That is the easiest one. So vertically, if we assume no air resistance, oh, I should write that down. We are assuming no air resistance. What happened if you got air resistance? Wait lah. We will see more of that in chapter 4. Okay, so what happens to the acceleration? What's affecting the vertical? Gravity, pulling stuff down, remember? Okay, so it's just our good old 9.81 here. So I should say negative 9.81. That's your acceleration. Downwards, ooh, I should define my direction. Very nice. So I'm going to define, let's draw a corner on the top right. Let's use our normal axis. To the top is positive. To the right is positive. So down is negative, left is negative lah. So this is downward acceleration, so I'm going to say negative 9.81. Okay, so that's that. And does it change? No. Your ball is in the air, it's in free fall, it's just going to experience an acceleration of negative 9.81 down. The negative just tells you it's downwards. How about velocity? Aha! So we have seen this before. Where did we see this? So the ball you throw, it goes up, it comes down. But then, if you only look at the vertical part, it's just the same as your object that you throw vertically up and come down. So this one is, like you know already lah, okay? Here is maximum height where velocity is 0. Maximum height of the basketball where v is 0. But what is this? Initial velocity. Now here is positive, right? Some positive value up here. So that is what we say it's going up, moving up. This first part. What's the initial velocity? Now we can break the components. So this initial velocity will be u sine theta. What happened here? Okay, so that's this point up there. And as the ball goes up, it gets slower and slower vertically. Eventually, the vertical velocity is 0. Now I must put there Vy already, otherwise you were confused. And then it will start to come down. The arrow we saw just now was pointing up, and then it pointed down. So this is where it's going down because you are in the negative section of the graph. So describe the ball is going down. Okay. So how do we draw the displacement graph again? Vertical displacement now, so you're only looking at the height of the graph. Don't care whether it moved to the left or to the right. What's the height? Well, we need some guidelines here. So I'm going to add. Okay, so this is for the projectile we saw just now. I go up, come down. One curve. And the maximum height is where? Right here. So this, when v is 0, that's when the maximum height is. So I have to, here, let me do a manual draw on. So I have to draw something of a quadratic like that. Oh man, something like this. Okay, so assuming that I define 0 displacement as the ground or the lowest point, okay, then I throw the ball up, highest point comes down. So to label up this graph a little bit, okay, reminder, here is your max height, which we can also just call h lah. I don't know, there's no particular formula for it, for h. Okay, so that's it. You say, me so easy, that's it. Yeah, this looks exactly like your vertical drop or vertical throw up of a tennis ball, because you're just looking at the vertical only, just the vertical. Now, if you want to be realistic, we go back to the video and say, wait, miss, what's the whole video? I thought the ball will bounce one. Yes, rebound. So if you look at the whole video, actually, you will find that, you see, I throw the ball, and you watch what happened. Whoop, boing, 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 boing. Notice how after each bounce, the ball gets shorter and shorter, but it's still running away to the right. So why is that? So let's be realistic. Let's include that in our challenge today. How would you draw this thing if you had rebound into the picture? And you need to remember that you're losing energy with each bounce. So something like this. Okay. So you can imagine this picture on the right is the basketball, like just now lah, just bouncing and running away with horizontal and vertical components. But it's the same as a ball on the left here, just bouncing up and down vertically without any horizontal. So you see? Same thing, right? Okay lah. So just keep this in mind. Bouncing, if we're losing energy, each bounce will get a little shorter. So how do we graph this? Very nice. Okay. Let's start with acceleration. Back again. Will the acceleration change? No. After each bounce, you're still on planet Earth, right? Did the Earth explode? No. Did the Earth become lighter? No. So, okay lah. Still the same acceleration. So, it's still 9.81. But if you want to be realistic, actually, there is a small spike here. Man, it's supposed to be like this lah, but very, very narrow. Okay. Why is there a spike? Because the moment when the ball hits the ground, something happens. A collision happens. That's what we will see more in chapter 4. Dynamics. Why is there a spike? Yes. Keep that in mind. We'll answer that in chapter 4. Okay, next up. We have our vertical velocity, but you notice something different? This is at a different starting velocity now. After it hit the floor, okay, this dotted line is where it hits the floor. Hit floor. That's the first hit. Something happens and you lose a bit of energy. That's because maybe your ball, the basketball, is a bit flat, not enough gas, or the floor is soft and squishy. I don't know, for whatever reason, okay, you will have some energy lost. And also, this one we will learn more about it in chapter 4. Why is there energy lost? Okay, but notice how the velocity is now smaller already. But the gradient is still the same. So I should make a note that here. Gradient is still slanted by the same amount. Why? Because your acceleration is still 9.81 and acceleration is your gradient. Or negative 9.81. Okay, so that is the velocity part. And that is the end of another bounce. Okay, you go up, another max height. I should label them all. Here, let me do this. Height 2. First one was height 1. Next one is height 2. Then it come down. So this part is down. Then this part is up. And that's the end of the second projectile. So each projectile is a bit smaller. And let's see. Let's draw a center line again to help us with drawing the displacement curve. So you've got those two. Now we need to draw our displacement curve. Now, just now you saw it's getting a bit lower. We're looking at the vertical only, just the y. So vertically you're high, then lower. So you draw something lower, like this. Can lah. Okay lah, and this height here will be our second maximum height after you've lost some energy. So a little bit lesser. And then we go on to the last one. Oh yeah, you can draw many lah, okay? Last one I'll just skip through. You can draw acceleration. You have another spike, probably a little smaller too. Why leh? You figure out also. Think about these spikes. Actually, exam won't ask you to draw the spike. In chapter 3. Okay, and velocity. Same gradient, but a little smaller velocity now. So now you're at an even lower velocity. Drop a bit more already. So you start off even lower, no? So once you hit the floor, okay, this is what's happening. The ball goes down, let's say at 10 meters per second. Hits the floor, pam. And then the ball goes up. But then at 8 meters per second. So you got some energy lost. Okay, that's where the energy loss is coming from. That's why the height of each triangle is not the same. And you have also the displacement graph. Yay. Okay, let's draw the displacement graph also. So, maximum height. Wow, my quadratic curve becoming more. This one. Yes, draw this. Okay, and you have the third height, even lower, height 3. And you keep going until you eventually lose all your energy lah. Okay, so this is respect to time, and time. Okay, but it's only the x component. Okay, it looks very similar to your vertical, single, one-dimensional vertical free fall. One more thing I would like to point out is, you notice, right? Remember, each bounce you lose energy. Notice the time interval here. Don't forget the time interval. Okay, the first time, from the time you throw up and come back down to the floor, is quite long. But then the second time, shorter already. You see? Third time, even shorter already. And you're limited. Why? Because firstly, you're traveling a shorter height. See? These heights are all getting shorter and shorter. But you're traveling at the same acceleration. So remember, your time is actually different. Okay, so that's your vertical part. How about the horizontal part? This part is new for us. Is it? Or is it? So just now we said this vertical part is just like a ball that you throw up vertically and come down. One dimension. How about the horizontal? Okay, let's draw the horizontal. I need to wrap off this part. So, okay, the horizontal is purely horizontal. We don't care about the vertical anymore. So when you're looking at the pure horizontal, what happened to the ball? Okay, I draw the lines first for you. So when you look at the basketball just now, it was moving to the right the whole time. Did it U-turn? No. Did it go to the left? No. So your basketball, all it did was go to the right. So that's something to keep in mind. Going to the right is what? Positive, right? So positive velocity. And when we look at the arrow changing, did the arrow change length at all? No. So your velocity, horizontal, is constant. That's our first clue. So how do we draw the horizontal acceleration? first things first, if your velocity is constant, you cannot have acceleration. There's no change. So it's just a simple, straight old zero acceleration there. Okay? That is based on the fact that there is no horizontal acceleration if we don't consider air resistance, negligible air resistance. Okay, because there's nothing, no forces acting on you, nothing to stop you, nothing to push you. All right, no wind blowing, nothing. And then okay, so we got our acceleration 0. Like that only. Okay, velocity. Yes, velocity. So you look on the left side. Wow, velocity got like triangle like that. How about the x component? Is moving to the left, constant speed. Constant speed means your graph will look like how? Constant speed. No change. Okay, so the horizontal part of the basketball is not changing in velocity. So it's just straight line. And if you want to label it, let's add some, let's say use green labels. Okay, sure. Oh, your initial velocity here will be ux, or what you can use as u cosine theta, which is ux. Okay, that will just be the same throughout from the beginning to the end of the entire journey, from 0 until I call this t lah. Same, no change. Okay, nothing too interesting here. Still the same thing. Last one, displacement. This one you must think about it. Displacement. The basketball starts on the left, moves to the right. You stare at it lah. Now I play for you again. Where is it? Here. Okay. So you start here. Basketball's on the left, right here. And then once you throw it, it's just moving to the right. The displacement from the original is to the right. Okay, so from the starting point where it was first thrown, how are you going to draw the displacement graph for that? Well, it's a constant velocity. And constant velocity means what? Constant velocity means you're just going away at a constant rate. So displacement is increasing at a constant rate like this. So at the beginning, you have 0 displacement. That's what we call define as 0. And then you move to the right at a constant rate until you stop at time t. Okay, so here you can make a reminder to yourself that this is constant velocity means constant gradient. What's the gradient of this? Gradient is the velocity, so your velocity is this one. So your gradient is u cos theta. Okay, it's just going further away. The longer time it is, the further the basketball will run away. And it's very tiring to chase the ball, okay? Alright, so that is this whole part about how you can think of both components separately when you're trying to graph them. Now, I will encourage you as you are learning to not memorize all these graphs, but to learn to draw them and what's the reasoning behind them. Why the shape like that? Why the graph like that? Why? So don't memorize because they can give you any scenario. Badminton, hit and then it fly. The person throw a rock off the building. How's the graph? Okay. It's based on the same ideas, but there are different scenarios. To wrap up today, I have a final bonus challenge for you. And that is the question. So we have all this graph. How would the kinetic energy of the basketball look like for one projectile, the first projectile? How will we think of energy of the basketball? There's kinetic energy. There's potential energy. So if we can look at some graph that looks like this. Yeah. How would you draw kinetic and potential energy graph on this thing? For reference, this is the end. This is the first bounce. Okay, so the end of the first projectile. How would you draw this? Think about it for a moment. So kinetic energy is something that depends on the speed of an object. So if you remember from previously, you learned before in IG or SPM or somewhere else, kinetic energy is calculated by half mv squared, right? And potential v is the velocity that the projectile is moving at the both components add together one. Mass is mass of the projectile. Potential energy is gravitational potential energy. So you can calculate that with mass. How heavy is the thing? How strong is the Earth's gravitational field? 9.81. And how high up is the ball? So think about this. Where will the ball move the fastest, have the biggest kinetic energy? Where will it move the slowest? Potential energy is the easier one lah. If it's very high up, it has high potential energy. So let's draw potential energy first lah. Okay. So potential energy, you can guess if your object is in ground level, right? Okay, the basketball bounce like this. Okay, you literally see the basketball move like this. Where is it the highest? Up here, lor. So up here is where you have maximum gravitational potential energy. So if you want to sketch a graph for that, I guess you could do something like this. Oh, I cannot do in one stroke. What's there? Ah, okay. So if we say 0, the ground is 0 potential, so 0 lah. And here is where you have the max height of the basketball. We're not going to do the bouncing thing, never mind. Okay, so at this time you hit max height. How about kinetic energy though? That's the one where students will find a little bit tricky. Let's go back to the animation earlier. From here, okay, so refresh, reset. Where is V the longest? This V, where is it the shortest? So let's fire. So here you see the beginning initial velocity quite long, oh. It's like a little bit shorter. It gets a little bit longer. It's a bit hard to see. But I want to think about it this way. At the beginning, there are 2 components that contribute to this V. So it's pretty big. In fact, it's the biggest. Then as you fire, Vy is getting smaller and smaller until at some point, can resume and pause. Missed it. Until at some point there is no Vy. Then we say maximum height. There's no vertical velocity at all. So it's only the horizontal component here that contributes to V. So here you can say the V is the smallest already. Oh, then what happened? Continue. Then V become bigger and bigger again. Oh, okay. You can go play around with this animation and stare at it more times. But just FYI, you start off with the biggest kinetic energy. So something like this. So here will be your half mv square. V includes both components. But then you will decrease at some point. Then you stop there. Why not go to 0 leh? Because at the highest point, do you still have velocity? Is the ball still moving? Of course lah, basketball is still moving at the highest point. It's still moving to the right. So at the highest point, you still have, although Vy is 0, Vx is still there. There's still a value and it's still the same as the beginning. So there's still energy lah. As long as you're moving, you have kinetic energy. So you can draw like this. And then you'll go back to the original, bit crooked graph here. Alright, so you see, it doesn't go down to 0. At the top, at the highest point, you will still have kinetic energy because you are still moving due to your Vx. Thank you, Vx. So let's label this. This is kinetic energy. And our blue color one was gravitational potential energy. This is a sneak peek of a further chapter that we will learn more about. This whole energy chapter is in chapter 6 to come. So it's a trailer for that. Alright, so that's all for kinematic graphs for projectiles. Just remember, it's the same old thing. Now it's split into X, split into Y. That's it. Alright, so have fun trying out some of these questions. All the best. Don't memorize. Practice drawing graphs. Go stare at some phenomenon around you. Throw a pencil and try to draw the graph. That's all for this section on graphs.